see my screen?
Yes, I do.
Okay, so the lecture I'm going to give today is about advanced optimizations for matrix multiplication. I'm using the template slides for the for the fourth edition of the book, but this lecture isn't in the fourth edition. It's actually a lecture that we are planning to introduce to in the fifth edition. So in the next edition of the book, this is going to be a new chapter. And this material is the material I'm going to cover today is going to appear in the next chapter. So you're kind of one of the first groups to see this new material, so I appreciate any feedback that you might have on this lecture after we go through it. Okay, so what's matrix multiplication? I think everybody here knows what that is. If I have I want to multiply two matrices A and B to get a matrix C. What we do is we have a matrix C and we have two matrices A and B, and every element in matrix C is going to be the dot product of the corresponding row in matrix A and the corresponding column in matrix B. And the way we parallelize this, or a very simple way to parallelize this, which I assume that you've seen in an earlier lecture in the course, is you can assign a thread to every output element in matrix C, and that thread can iterate through the row of A and the column of B, do the dot product, and store the results. This is a very simple way of parallelizing it. Of course, this is not the most efficient way of parallelizing this, and to do that, let's just analyze how this implementation behaves in terms of accessing the memory. So if we look at if we calculate the arithmetic intensity of this kernel, we find that it comes out to be memory bound. So in this kernel, what every thread does is it's loading two values from global memory and then it's multiplying them and then doing an addition operation. So we're loading two values. Each value is 4 bytes. That's 8 bytes, and we are doing two floating point operations in multiplication and addition. So we have 2 over 8. Our arithmetic intensity is 0.25 floating point operations per byte. Of course, I'm ignoring it. You also have a store that you do after the loop. I'm ignoring that because it's negligible compared to the amount of memory that we load. So you can see, so 0.25 floating point operations per byte is very low compared to the kind of arithmetic intensity that you need to be compute bound on a modern GPU. Like on an H100 GPU, for example, you would need around 20 floating point operations per byte to be compute bound. Now, in practice, this arithmetic intensity would be higher because of caches. The caches do a fairly good job at keeping some of that data close so that you don't actually go to global memory every time you load. But still, even with the caching, you tend to be, if you don't have any kind of manual interventions and optimizations, this implementation will still be memory bound on a modern GPU. But we know that matrix multiplication is fundamentally compute-bound computation. So let's look at the potential for matrix multiplication in terms of its compute-boundedness. So matrix multiplication has the potential to be highly compute-bound. That's why it's such a successful computation on GPUs. If we have an n by n square matrix, for example, let's assume we have a perfect implementation that loads every input value that it needs only once. The amount of data or loads or stores, so accesses, the amount of data that we would need to access is going to be, we have 3 matrices, we're loading 2 input matrices, and we're storing the third one. Each one of these matrices is n by n, so we have n squared values, and every value is 4 bytes. So we're going to have 12 n squared bytes that we need to access. The number of operations that we're going to perform are n cubed times 2. So we have n squared is the size of the output matrix. And for each one of those elements, we're going to do n multiplications and n additions to do the dot product. So we end up with 2 n cubed floating point operations. And if we take the ratio of that, we end up with 0.67 n operations per byte. So a perfect implementation that loads every value or stores every value it needs only once can achieve this kind of arithmetic intensity. So if we have a 1024 by 1024 matrix, for example, and somehow, it's not realistic, but somehow we were able to load every value that we need only once and reuse it as much as we need it, we can get 171 operations per byte. So you can see that this is much higher than 20 operations per byte, which you need to be compute bound on a modern GPU. So we have the potential to be highly compute bound when we execute matrix multiplication on the GPU. And then the question is, how can we achieve that? Now, you've already seen, and I'll review it quickly, you've already seen shared memory tiling as one way to increase the arithmetic intensity. So what happens with shared memory tiling is, let's say a thread block is assigned to this colored output tile over here. What we do is we are going to divide the input matrices into tiles, and we're going to load the tiles of the input matrices one pair of tiles at a time. So let's say we have this pair of input tiles over here. We're going to load those from global memory to shared memory. And then once they're in shared memory, what we do is we have the threads that are responsible for this output tile use the values from shared memory to compute their contribution to its own element. And usually this output tile is in registers, right? Every thread is going to have this accumulator where it accumulates the result of the dot product in some kind of register. Now, the advantage of shared memory tiling is that instead of this thread loading each one of these input values from global memory every time, or sometimes it'll hit the cache, but there's no guarantee to that. We're loading it from shared memory. So we load each one of these values once from global memory to shared memory, and then we reuse it across the threads that need it. So let's calculate what improvement to arithmetic intensity we have if we apply shared memory tiling. So over here, let's say we have an n by n output tile, and we are iterating through input tiles that are also each n by n in size. So if we have n by n squared tiles, we need to load two input tiles. So we have two input tiles. Each one of them has n by n values, so n squared values, and each value is 4 bytes. So we have 8 n squared bytes. And again, I'm ignoring the store just because it's negligible, because we load many input tiles and then we finally store one output tile. So I'm neglecting it for now. And then in terms of the operations that we do, so once I load these two input tiles and I want to calculate their contribution to this output tile, we're going to do n by n dot products, and each dot product is going to be of size n. So we have n squared dot products, and then if we're going to do n adds and n multiplication, so that gives us 2 n cubed floating point operations per byte. And we get when we take the ratio, we get an arithmetic intensity of 0.25 n, lowercase n, floating point operations per byte. Now, usually in a simple implementation of shared memory tiling, what we do is we are going to have 32 by 32 tiles, just because the largest block that you can have on a GPU is 1024, which is 32 by 32. So if you do a simple approach of assigning one thread to every output element and one thread to every input element that you're loading, then you're going to have 32 by 32 tiles, and this gives us 8 floating point operations per byte, which is good, right? But still, and in practice, it's going to be larger because of caching again. But still, 8 floating point operations per byte, it's much higher than 0.25 floating point operations per byte, but it's not in the range where we fully utilize the compute resources of the GPU because we're compute bound. Remember, for an H100, for example, you need around 20 floating point operations per byte to be able to kind of be in the compute bound range. So the question is, how can we increase this ratio? And clearly, right, if I want something higher than floating point operations per byte, what I need to do is I need to increase n, right? In other words, I need to increase the sizes of these tiles in order for me to be able to get better arithmetic intensity, in order for me to push the implementation into the compute bound range so that I can fully utilize the GPU resources. Now, what does increasing n mean? Well, if these two input tiles are going to be placed in shared memory, and this output tile is going to be placed in registers. So increasing n means I'm going to need more shared memory for my input tiles, and I'm going to need more registers for my output tile. And we all know that there's a limited amount of shared memory, and there's a limited number of registers that you can have on an individual SM. And therefore, there's a limit to how much we can increase n before we run out of resources. Okay, So let's see first how we can increase n and what our limits are going to be towards increasing n. Okay, but the main idea here is that increasing n improves the arithmetic intensity. Any questions so far about the arithmetic intensity analysis? Is everything clear? Okay. So before I look at how we can implement a kernel where we increase n, so far I've been assuming square tiles, but let's not assume square tiles. Let's assume that we have an m by n tile. And then let's assume that each one of our input tiles, this one is going to be m by k, and then this one is going to be k by n. Okay, and let's redo our arithmetic intensity analysis with this in mind. So over here, if we look at how much data we need to load from the global memory to the shared memory, we have an m by k input tile and a k by n output tile. So that's m by k plus k by n values, and each value is 4 bytes. So in total, I have 4 m times k plus k times n bytes that I need to load. Again, I'm ignoring the bytes that we need to store because we do this many times in a loop, but we only do the store once at the end. So we can ignore it. And then finally, the operations that we perform, we have m by n output elements. So that's m by n dot products. And each dot product is going to be k multiplications and k additions. So we have m by n by k by 2. That's the number of floating point operations that we're going to perform. So if we take the ratio of these, we get 0.5 m by n over m plus n floating point operations per byte. Okay? And the interesting thing about this ratio is that k is not included in the ratio. So k, this is the width of this tile and the height of the second tile input tiles. K is not part of this ratio. Okay? And the intuition is that to increase the arithmetic intensity, I want to take a value that I loaded and I want to reuse it as much as possible. In other words, I want my output tile, so m by n are the dimensions of the output tile. I want my output tile to be as large as possible so that any input value that I load, I reuse it as many times as possible to compute different elements of the output tile. But having large input tiles is not exactly impactful for increasing my arithmetic intensity, and that's the intuition behind why k does not appear. And what that means is that if I want to increase m and n without straining my shared memory, what I can do is I can simply make k smaller, right? I can make k small. So if I make n 4 times larger, I could make k 4 times smaller, and that way I haven't increased the total amount of shared memory that I'm using for my input tiles. So just to recap on what I said, increasing m and n improves my arithmetic intensity, and I don't need to increase k. So what we can do is the intuition is that having large output tiles allows us to reuse the same input value to compute more output values, and there's no advantage of having large input tiles. So what we can do is we can keep k small, and this prevents us from straining the shared memory. However, what we do put strain on when we increase m and n is the registers. Okay, remember every thread places these accumulators in its registers. And if I'm increasing m and n, if I'm increasing the output tile, every thread is going to have to be responsible for multiple output elements, and therefore it's going to have to use multiple registers to store its portion of the output tile. We're going to see this later on. So we're going to have higher demand on registers overall. Just to give you an idea of sizes, typical values that we might use for m and n are 128, right? So we can have a 128 by 128 output tile. And with 128 by 128, this gives us a reuse rate. If we plug that in over here, we'll get a reuse ratio of around 32 floating point operations per byte, which does put us in the compute bound range on a modern GPU. Okay. So next, I'm going to look at how to actually, so like I said, the typical sizes are 128 by 128. And over here, we have 128 by 8 and 8 by 128, because if that comes out to be 1024 elements or 4 k bytes, which we have plenty of shared memory to accommodate that. Okay, so before I get into the implementation of how we do this, does anybody have any questions?
Well, I do actually.
Yeah.
So you said that like it doesn't matter how uh, if 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 cow is a small if k is a small or large, right?
Mhm.
So can we select? Is it practical to select k equal to 1, or it doesn't
That's a,
matter again?
that's a great question. So it doesn't matter, but you still want to select a K where when you want to load these values, you don't underutilize your cache line.
Oh, okay.
Okay, so you don't want K to be too small because if this is stored in a row major order, you want to be able to kind of when you access this row of the tile, you want to be able to fully utilize your cache line. You don't want to load a partial cache line.
Mhm.
So yeah, you don't want to make K too small
Okay, but
in that sense.
theoretically it doesn't matter, right? But practically, k should be like not too small.
Yes, yes, for cache consideration purposes, exactly.
Okay. All right. Thank you very much.
Yeah, thanks. Any other questions? Okay, so now let's talk about implementation details. Well, basically what we need to do is we're going to have to iterate through these input tiles one pair at a time. We're going to have to load the two input tiles from the global memory to the shared memory. Okay, so I'm going to use BM. So here we have M by K and K by N to indicate the size of the matrices. I'm going to use BM and BK to indicate the size of the tile that we're going to load for the whole block. Okay, and BK by BN as well to indicate the sizes of the tiles. So for each iteration over the tiles, we're going to load the input tiles from global memory to shared memory. And then every thread is going to be responsible for a bunch of elements in the output tile, right? So every thread is going to have its own thread level output tile. And that thread is going to go through the input elements in shared memory to compute their contributions to its output tile. The typical sizes here, again, we have 128 by 8. Here we're going to have 8 by 128. And then this output tile is going to be 128 by 128. And for reasons we'll talk about later, because we use a lot of registers, we can't have full occupancy. So typically a thread block is going to have 256 threads. What that means is we can have a 16 by 16 thread block. And if I have a 128 by 128 tile divided across 256 threads, every thread is going to have to take around 64, is going to take 64 elements. So every thread is going to be responsible for an 8 by 8 output tile. And remember, this 8 by 8 output tile is going to be in the registers. So every thread is going to have 64 registers that it dedicates to store these output accumulators. Okay? What does the code for this look like? So this is a kind of a kernel that implements the strategy that we just discussed. First, every thread block is going to identify what output tile it's responsible for within the output matrix. Then every thread is going to kind of identify what output tile it's responsible within the block's output tile. So this is identifying the thread level tiles. Then every thread is going to declare a TM by TN or an 8 by 8 output tile that it's going to use to accumulate its output elements. We're going to clear that, and then we're going to iterate over the input tiles, one input tile at a time. Here we're going to load the two input tiles A and B from global memory to shared memory. We sync threads to wait for the loading to finish. And then every thread is going to do a matrix multiplication of the two input tiles to calculate the value of its output tile. We sync threads again, and we keep iterating. And then once we're done, every thread is going to write its output tile from the global memory, from its registers to the global memory. Okay, so I'm using multiple helper functions here. There's the clear function to initialize the tile to 0. We have loading a tile from global memory to shared memory. We have the matrix multiplication, and then we have writing the tile from the registers to the global memory. And next, what I'm going to do is I'm going to look at each of these helper functions and how they're implemented. But any questions about this high-level code, I think should be fairly clear if you've implemented a shared memory tiling for matrix multiplication already. Okay, let's start with declaring and initializing an output tile. So the way that we declare, we want to have an 8 by 8 output tile for each register, for each thread. So the way that we declare the output tile is like this. We're going to have float, we're going to give it a name. We're going to call it CR here, just indicate it's matrix C, it's in the registers, and these are the sizes. But what we know is that by default, when you declare a local array like this does not go in the registers. This goes in the local memory, right, which ultimately gets placed in the shared in the global memory and gets cached. But what we want to do is we want the compiler to promote this local array into the registers. And for the compiler to be able to promote the local array into the registers, its size has to be constant. And all accesses to this local array have to have constant indices. So the way that we do that is whenever we're going to iterate over this array, we're going to unroll those loops so that when you unroll the loops, you're no longer using a variable index, you're going to be using a constant index to access this array. And by unrolling the loops, that's how we make sure that the compiler eventually places this local array into the actual registers. Okay? So loop unrolling, the variable indices become constant indices, which allows the compiler to promote this to registers. So for example, this clear function right here is going to iterate over this array, and it's going to just initialize it all to 0. So we're going to have a loop that iterates over the rows of the array, a loop that iterates over the columns of the array, and then initialize it to 0. But by putting a pragma unroll over here and making sure that the loop bound is constant, so here m and n are going to be defined as constants in the earlier parts of my code, okay, or it's going to be template. It's going to be a template parameter. This ensures that these loops get fully unrolled, and then this CR is placed inside of the registers. And you're going to see later on that whenever I iterate over this array, I'm going to make sure to unroll those loops in order for the indices to always be constant. Is that clear? Questions? Okay, so next we have loading the tiles from the global memory to the shared memory. So we have this load tile function that we need to implement. So the idea of loading the tiles is that we have this tile in global memory and we want to load it into the shared memory. But remember, the typical size for this tile is going to be 128 by 8, so that's 1024 elements. But recall that in my thread block, I'm only going to have 256 threads. And what that means is that every thread is going to have to load 4 elements, okay? And now what we want to make sure that the accesses are coalesced. So what we're going to do is we're going to divide this, and we're going to improve this later on. But for now, we're going to divide this input tile into 4 subtiles. And we're going to have the threads iterate over the subtiles and load each subtile in a coalesced way, okay? So this is what this function load tile over here does. It takes the address of A in shared memory, in global memory, and then where we want to put it in shared memory. It takes the leading dimensions to be able to do the indexing, and it takes the height and the width of the tile. And then over here, we calculate how many subtiles we have. In this example, it's 4 subtiles, and then we iterate over the subtiles. We calculate the index of the element within the subtile that every thread needs to load. And then we load the value from global memory to the shared memory. And of course, we have a boundary check so that if this tile is somewhere close to the boundary, the elements that are out of bounds, we just write a 0 instead. Okay, so this is how this load tile function works. Now, just to see how we call this function and what parameters we pass to it. So again, we're loading from global memory to shared memory. So what does this load tile function need? It needs the address of the array in global memory. That's what this is, right? It needs the leading dimension so that it can index this array. So that's K right here. It needs the bounds to make sure that we're not out of bounds over here. It needs the horizontal bound to make sure we don't access anything out of bounds. It needs the address of this input or this out where we're loading to in shared memory. It needs the leading dimension for this array, and of course, it needs the dimensions for the tile that we're loading. So these are what we are passing to this load tile function in order for it to load successfully. Okay. I'm not going to go through the kind of the details of the indexing. It's a little tedious, but I think if you're already familiar with shared memory tiling, you should be able to figure out these indices on your own. Okay, so this is how we implement this load tile function. Next, we go to the matrix multiply. So with the matrix multiply, now we have our tiles in shared memory. And what we need to do is we want every thread to do a matrix multiplication of its portion of the input tiles to calculate their contribution to the output tile. Okay. So here we're going to call the matrix multiplication. We're going to pass to it the dimensions of the output tile that we are calculating. We're going to pass to it the inner dimensions. This is basically the how long the size of the dot product. So this is the inner dimension of the input tiles to know how long it needs to iterate to do the multiply and add. We're going to pass to it the starting address of the first input tile and the leading dimension of the first input tile, the starting address of the second input tile and the leading dimension of the second input tile, and finally we're going to pass to it the starting address of the output tile. Of course, this is a starting address, but once all the code gets inlined and all this will be promoted into registers, it's not going to have an address anymore. It'll all get promoted into registers. But this abstraction kind of helps us with the coding. Any questions? Now, the implementation of matrix multiplication is very simple. It's just three nested loops that iterate over the output elements and then iterate through the input tiles and do a multiply and add. Okay, so if there are no questions, now let's talk about writing the output tile. So once all the threads are done computing their output tiles, so they're done iterating over all the input matrices and they finish computing their output tiles, they need to write their output tile from their registers to the global memory. Okay, so for that we implemented a write tile function, and this write tile function so this write tile function takes the addresses of the input tile and the output tile and simply just iterates over the input tile, this input tile right here. So it iterates for every row, for every column, and again we unroll them to make it into registers. Does a boundary check, and if the value is within bounds, it simply writes it from the registers to the global memory. Okay, so this is a simple function to implement. How we call it, so what we need to pass to this function is the starting address of the threads tile in the global memory. So there's some involved index calculation here where you use the starting address of the blocks tile and you add to it the starting address of the index of the threads tile. You multiply that by the leading dimension, and then you also include the column, the row and the column of the blocks and the threads. So that's how you get the starting address of the threads output tile in global memory. You need to find, you need the leading dimension of the output tile. You need to have the bounds. So here we make sure that we pass the bounds so that if our output tile somehow lies on the boundary and some of it is out of bounds, we make sure we don't do any out of bounds accesses. And of course, the starting address of the threads output tile. And again, once this gets inlined and unrolled, right, this is going to become registers. But the address is just helpful for the abstraction. And of course, the height and the width of the output tile that we are writing. Okay. So this is how we implement this write tile function. Okay, I know this was a little tedious going through the code, but I just wanted to make sure that we go through some of this just so that you have an idea of what's going on, so that once we move on to discuss the other optimizations. But I'll do less code and more conceptual optimizations going forward. Any questions before I move
on? Just another question from me. So, well, like when it comes to different GPU models, where like they have like different kind of like number of registers, do we need to tune this algorithm like for a specific model, or it can be like scalable depending on the GPU hardware?
So yes, of course, different GPUs, they're going to have different shared memory resources, and depending on how many registers you have in shared memory, for example, different SM resources. So depending on how much shared memory, how many registers you have on the SM, you will need to tune these values, of course. Another thing is if you're using different precision. So everything I've been doing here has been assuming FP32, right? So 4-byte values. But if you're using different precisions like 16-bit or 8-bit, the elements are going to be smaller. So the number of elements that you can accommodate is going to be larger. So these dimensions will also differ depending on the precision that you're using, even within the same GPU.
Okay. And by the way, can we offload this kind of computation that you're doing in the registers to the tensor cores?
Yes, I'll talk about that
Okay.
later. Of course.
Right.
Of
Okay,
course we
thank you.
can. Yeah, thank you. Other questions? Okay, so now let's talk about optimization. So there's a number of optimizations that we can still apply to make sure this implementation is more efficient. Yeah, some of you probably picked up that there were certain things that we were already doing that were not very efficient when it comes to memory accesses. So let's talk about these computations. So one is vector loads and stores. I don't know if you've covered vector loads and stores, but that's basically when a thread, instead of loading 4 bytes, it can load or store 4 bytes, it can load 16 bytes at a time. We call that a vector load, or store 16 bytes. We call that a vector store. Another one is register tiling. So this is when you become bound by the shared memory access latency. You want to make sure to reuse values that you load from shared memory as much as possible to avoid going to shared memory every time. Making sure our stores are coalesced. So far, they haven't been coalesced. So we want to make sure that those stores are coalesced. Bank conflicts when you access shared memory. So we're going to talk about those. Another one is software pipelining and warp specialization. So that's something we're going to talk about as well. This is particularly important in tolerating the fact that we are going to be working at low occupancy. And we're going to cover that when we talk about software pipelining. And then finally, using specialized hardware units like the Tensor Memory Accelerator and the Tensor course. Okay, so for the rest of the lecture, I'm basically going to go through this list of optimizations and see how we can apply them within the context of this matrix multiplication implementation that uses these large piles. So let's start with vector loads. So if you go back to when we were loading our input tile from the global memory to the shared memory, we said that we have 4 times as many elements that we need to load as we have threads. So our kind of initial naive implementation was to iterate over the input. We to divide the input tile into subtiles and iterate over it one subtile at a time, and then load each subtile on its own from the global memory to the shared memory. Okay. Now with vector loads. So without vector loads, so what we were doing before for scalar loads, if we track what one thread is doing, this thread, for example, it's going to load this for the first subtile, it's going to load this 4-byte value from the global memory to the shared memory. Of course, the thread adjacent to it's going to load the next value. The thread adjacent to is going to load the next value. So these loads will be coalesced. Okay. But then it's going to load this value, then load this value, then load this value, then load this value. So this thread is going to do 4 load instructions and the index calculations that are associated with it. And each load instruction is going to load one element, which is 4 bytes. Now, we know that GPUs let us do vector loads, where every thread can actually load 4 4-byte elements, or 16 bytes. So with vector loads, instead of the thread iterating over these 4 elements and loading them one at a time, what the thread can do is issue one vector load instruction and load 16 consecutive bytes from the global memory to the shared memory. So in this case, what every thread, instead of dividing our output tile into 4 subtiles, we're just going to, our input tile into 4 subtiles, we're going to treat the input tile as one large tile, and every thread is going to load 4 consecutive elements of that tile with one single load instruction. Now, what's the advantage over here? The main advantage is that we are loading more data with fewer instructions. But both of these result in coalesced memory accesses. So we're not impacting the coalescing, right? But what we are impacting is that instead of having to do 4 load instructions to load 4 different values, we are able to load 16 bytes using just one instruction. And that allows us to kind of send memory requests to the memory system at a faster rate. And this is going to be important because we're operating at low occupancy. And I'll come to this point later. Okay, is this clear? Okay, so vector loads are useful. Now, vector stores are going to be even more useful because remember, we said that every thread is responsible for this 8 by 8 output tile. Now, if you think of what happens when we are storing these when the thread, remember when we did the write tile function, the thread was iterating over these elements in its registers, and it was writing them from its registers to the global memory. Okay. Now, if you think of what happens so when we do scalar stores, every thread is going to iterate through its 8 by 8 output tile. So it's going to issue 64 store instructions. And every store instruction is going to write 4 bytes. And if you think what threads in the same warp are doing, you're going to have this thread is going to write these 4 bytes. And then the thread next to it in the same warp are going to write these 4 bytes that are 8 elements away. Okay, so they're far away. So the scalar stores, we're going to have 64 scalar stores. Each store is going to store 4 bytes, and the coalescing is going to be poor. Whereas when we do vector stores, what every thread is going to do is it's going to use a vector store to store 4 elements in one instruction. What that means is that instead of having to do 64 scalar stores, we're going to do 16 vector stores, right? We're going to do four elements at once, or 16 bytes at once, okay? And each store is going to store consecutive 16 bytes. So there's 2 advantages here. The first advantage is that we're going to store more data with fewer instructions, right? So we have less instruction execution overhead. And again, this is important. We're going to see why this is important later on because we operate at low occupancy. But then another advantage is coalescing. So we have better coalescing because now this thread is going to store these 4 consecutive bytes. We're going to skip these 4 consecutive bytes, and then the thread that's next to it in the same warp is going to store 4 consecutive bytes. So the coalescing, we're still not perfectly coalesced, but the coalescing is not as bad as it was before. Okay, is that clear? Any questions? And later on, we're going to improve on this. So we're going to make this even better later on. We're going to have better coalescing than we have over here. Because right now we still have this gap between these 2 consecutive threads. Any questions? Okay. So now let's talk about register tiling. Remember, we said that once we, in our initial implementation, once we loaded our input tiles into the shared memory, so here I have A and B tiles inside of my shared memory, every thread is going to iterate through its output elements, and for each output element, it's going to iterate through the input tiles and load these elements from shared memory and calculate their contribution to the output element that's currently computing. But one thing we notice is that every element that we load from shared memory is actually used to calculate multiple output elements. So this input element over here, this thread is going to load it multiple times to calculate each of these output elements. So the thread is going to load the same element from shared memory multiple times. Similarly, this element right here is going to be loaded from shared memory multiple times for each of these output elements, right? Now we know that shared memory is fast, right? Shared memory is faster than global memory. However, once all your data is in shared memory and you're doing everything in the SM and you're not touching the global memory, the shared memory all of a sudden becomes slow relative to the other things that you are doing, right? So there's something that's faster than shared memory, and that's the registers, right? So the idea is that instead of loading this value from shared memory multiple times for each of these output elements, what I'd rather do is I'd rather load it once and reuse it for computing each of these output elements. And to do that, we're going to use the same strategy we used to minimize accesses to global memory, which is we did tiling in shared memory. We're going to do the same thing, but this time to minimize accesses to shared memory, we're going to do tiling in our registers. So what we're going to do is for these segments of these sections of the input tiles that the thread is going to access, we're going to iterate through them in strips. So we're going to iterate through our input tile one strip. So every thread is going to iterate through the input tile one strip at a time. And for each strip, what the thread will do is it's going to load these input elements from the shared memory into its registers. So it's going to declare kind of a strip, a local array that will eventually get promoted into registers. It's going to load these from shared memory to registers. It's going to load this strip from the shared memory to the registers. And then for these output elements, it's going to calculate the contributions of these two strips into all of these registers. So it's kind of like doing an outer product. Okay. So the typical size of this is going, so remember, this is 8 by 8 typically. So this is going to be an 8 by 1 strip. This is going to be a 1 by 8 strip. And then this is going to be an 8 by 8 output tile. And all of these are going to be in registers, right? Which means that the thread is going to load the strip to registers, it's going to load the strip to registers, and then the thread is going to iterate through all of these output elements and find the corresponding input elements, do a multiply, and do an add. And of course, the loops will get unrolled. Everything will get promoted from local arrays to registers. And this operation right here, this outer product operation, is going to be all done using registers, which means you're basically going to have 64 multiply and add operations in your code, one after the other. Okay, and as you can imagine, if you have 64 multiply and add operations one after the other, this is what lets you fully utilize your compute resources on the SM. The fact that you're not spending a lot of time accessing memory anymore. You're not spending a lot of, you got rid of your for loops, the branch instructions, because you got rid of your for loops, and you just have multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. And this is what allows you to reach that high compute utilization with matrix multiplication. Is this clear? Any questions?
Yeah, just another question from me.
Mm-hmm.
Is there any reason that we don't use like square tiles here? Like similar to what we did for like the shared memory tiling?
Wait, so we are using, do you mean a square output tile or the strips?
Input tile, yeah.
Oh, so the input strip, again, we want to use as few registers as possible. So just like we want to save on how much shared memory we use for the input tile, we want to save on how many registers we use for the input strips. And that's why we are going to load from shared memory to registers one strip at a time.
Yeah, I mean, why we don't consider the strips to be like square, not like this rectangular?
Oh, because if the strip was square, I'm going to need more registers to store it.
Yeah, but what if we like choose it such that it fits the register file?
But registers are a very scarce resource here. You're going to see we're already, so think about it. We're using 64 registers already for our output elements. And we've added 8 registers here, that's 72, and 8 registers here, that's 80. So this operation on its own is using 80 registers. We need 80 registers just for the input strips and the output tile, right? And of course, the code uses all kinds of registers for all kinds of other things like intermediate values, especially that we're doing unrolling. So we are really constrained for how many registers we have when we are doing this operation. And that's why we want to conserve registers as much as possible. So we're going to make these strips as thin as possible.
Okay, I see that. Thank you. Yeah.
Yeah, welcome. Okay, any other questions? Okay, so now we've seen how we do register tiling. Let's now talk about coalescing the store instructions. So remember, we improved coalescing by using vector stores. Okay, so every thread is going to do a vector store where it's going to store 4 consecutive values. Okay, but even with the vector stores, the writes from the registers to the global memory are still not completely coalesced. Why? Because if you think what adjacent threads are doing, this thread is going to store these 4 consecutive elements to global memory. And then you have a gap of 4 elements. And then you have the next thread is going to store 4 consecutive elements. So this gap, right, it means that you're not fully coalescing your stores. Okay. So the problem is that a vector store can store up to 4 consecutive elements, which is 16 bytes, right? So we can store up to 4 consecutive elements, but the tile width is 8. Okay, and the next thread is going to have another 8. Okay, so because the tile width is 8, but we can only store 4 consecutive elements, This is where this mismatch comes from. In order for me to fully utilize to fully coalesce my operation, what I need to have is I need to have this thread store 4 consecutive elements, and the next thread be responsible for the next 4 consecutive elements, and the next thread be responsible for the next 4 consecutive elements, which means that my tile should not be 8. My tile should be 4. The width of my tile should be 4, not 8. Okay? However, we've seen that in order for us, we want the tile to be as large as possible. We want threads to have an 8 by 8 tile, because the larger the tile, the higher the arithmetic intensity. But the fact that my tile is 8 in width is causing problems. I'd rather it to have 4 to be 4 in width so that I can coalesce my stores. So what we're going to do is we're going to rearrange the thread tiles so that instead of the thread being responsible for a monolithic 8 by 8 tile, the thread is going to be responsible for multiple 4 by 4 tiles. Okay? And what that does is that it allows a thread to still have 64 elements that it's responsible for computing, to still benefit from that high arithmetic intensity, but at the same time allows it to have coalesced stores. Okay, so let's see how we are going to rearrange the tiles to achieve this. So now we're going to talk about warps. What we're going to do is we're going to divide this output tile across warps. Every warp is going to take a certain, remember, we have 256 threads, so that's going to be 8 warps. So every warp is going to have its own output tile. So every warp is going to, so from this 128 by 128 block output tile, every warp is going to have a 64 by 32 warp output tile. Okay, and now when the threads iterate through the input strips, in order for them to compute their output tiles, you can think of threads in the warp as collectively, this is just logical, but you can think of the threads in the same warp as collectively iterating through the input strips as they compute their individual portions of the warp output tile. Okay? So you think of every warp has an output tile, and every warp is going to iterate through the shared memory one strip at a time. Okay? Now that we've seen what warps are doing, this is the warp, this is the block output tile. This over here is the warp output tile. The warps are iterating through the one strip at a time. Now let's zoom in on how the warp is going to divide its work across threads. Okay. Remember, we said that we don't want the threads to be responsible for a monolithic 8 by 8 output tile, because that is causing my stores not to be coalesced. So instead, what we're going to do is we're going to divide the warp output tile into 4 quadrants. And we're going to have so if I have a 64 by 32 warp output tile, every quadrant of the warp is going to be 32 by 16 elements. And then every thread is going to be responsible for a 4 by 4 tile inside of each quadrant. Okay? So instead of the thread having a monolithic 8 by 8 output tile, it's going to have 4 output tiles that are each 4 by 4 in size. Okay, and now what the thread, so now you can think of the thread's 8 by 8 output tile, its logical 8 by 8 output tile, as being composed of these 4 by 4 output tiles that are coming from different quadrants. So this is what a block does. This over here, this is how a block divides things across warps. This is how a warp divides things across threads, and this shows you the threads. And you can think of now these strips that every thread is loading. Instead of it being a contiguous 8 by 1 strip, it's going to be 2 separate 4 by 1 strips that are loaded from different parts of the shared memory. Is that clear? Any questions? So now every thread is going to load 4 values from here, 4 values from here, 4 values from shared memory to the registers, 4 value from here from the shared memory to the registers, and then every thread is going to calculate the contributions of these values to its output tiles. And then now, when the thread is done and it wants to store these output tiles from its registers to the global memory, when it does a vector store, the vector store stores all these elements of the output tile, on the width of its subtile of the output tile in one store. So if you can think of the threads, when the threads of the warp are storing this quadrant of the warp output tile, every thread, the adjacent threads are going to store adjacent chunks of 4 elements. And this gives you coalesced stores when threads in the same warp are storing the output tile. So the threads in the warp are going to store this quadrant all together in a coalesced way. Then they store this entire quadrant in a coalesced way, then this quadrant in a coalesced way, then this quadrant in a coalesced way. Is that clear? Any questions? Okay, great. So now we've kind of figured out how to make our input axes coalesced and as use as few instructions as possible with the vector loads. And now our writing of the output tile is coalesced, and we're using vector stores to write them out. And also our computation is very efficient because we are bringing the values to registers, and then most of our computation is happening directly inside of the registers. Okay. We have one more optimization at the kind of at this level of the memory axes, and then we're going to talk about occupancy issues. So the last one is eliminating bank conflicts. So bank conflicts, I don't know if you're familiar with bank conflicts. The bank conflicts basically occur when multiple threads are accessing shared memory and their elements fall into the same memory bank, right? The shared memory has 32 banks. So the data in the shared memory is stored in different banks, and you could have multiple elements be in the same bank. So if the threads are not making contiguous access to shared memory, they're accessing shared memory in a strided way. You could have multiple threads try to access values from the same bank, and then they have a bank conflict, and you can't serve both values. You have to serve one value and then the other, and this slows down the access to shared memory. So let's see if we have any bank conflicts and what we can do about those bank conflicts in our implementation. So here, let's focus on this first input tile. Okay, so on the first input tile, we're loading it from global memory to shared memory. That's great. And then over here, when we want to this here is just logical, right? So this input strip for the warp is in shared memory, and then every thread wants to load its portion of the input strip from the shared memory to the registers. So you can think of different threads are all trying to load their strips from shared memory to registers. Let's see what happens when these threads try to load registers. Let's focus on one quadrant for now. And let's see when the threads in the same warp, when they're trying to load this input strip for this quadrant. Okay, so these are the threads in the warp. Okay, every thread is responsible for a different 4x4 output tile in the quadrant. Okay, and every thread wants to load 4 consecutive elements from shared memory to their registers. Okay, so these threads, thread 0, thread 1, thread 2, and thread 3, they want to load the strip that goes 0 to 4. Sorry, 0 to 3. So they want to load elements 1, 2, and 3. So over here, the threads that are in the same row of the quadrant, they're going to load the same 4 elements from here. Okay, so these threads are going to load the same 4 elements in the strip. Okay, so when they're loading the first element, for example, index of that element, if we think of this whole input tile being in shared memory, okay, and we want to load this strip of the tile from the shared memory to the registers, okay, these threads are going to load elements 0, 1, 2, 3. These threads are going to load elements 4, 5, 6, and 7. These threads are going to load elements 8, 9, 10, 11, etc. Okay, remember this file is going to be stored in row major order inside of my shared memory, and the width of the tile is 8. Remember, this is a 128 by 8 output tile. So load a strip. The first element is going to be at index 0. The second element is going to be at index 8. The next element is going to be at index 16. The next element is going to be at index 4. So these threads are going to load elements 0, 8, 16, and 24. These are going to load elements 32, 40, etc. Okay, these threads load the elements starting at 64. These are going to load the elements starting at 96, etc. So when we look at when each thread goes to load the first element that it's going to load from shared memory into its input strips, these four threads are going to load the element 0. These threads are going to load element 4 in the strip, which is going to be, but every row is 8 elements, so it's going to be element 32 in the whole input in the whole file. This thread is going to load element 64. These threads are going to load elements 96, element 96, etc. Now, if we look at which banks these elements fall into, they're all going to fall into bank 0. Okay, all of them are multiples of 32, right? The elements are strided way across the banks. So you from 0 to 32, and then you go back to 0 to 32, and then go back to 0 to 32, etc. So all the elements at index 32, whose index is a multiple of 32, are going to go in bank 0. So what happens here is that when these threads in the same warp go to load this element from the shared memory, they're going to experience a bank conflict. Right? All of them are the same bank, so we can't serve them all at the same time. So we're going to serve them one after the other. And this means the shared memory access is very slow. Okay? So to avoid this bank conflict, what do? We want to make sure that these elements are not all at multiples of 32. We don't want these elements to all be 32 away from each other. So typically, the way we solve bank conflicts is by adding padding. So even though this array has width 8, what we can do is we can add an element of padding to this array that we don't actually use. It's an empty value. But what this does is that it makes this next element, rather than being at index 8, it's at index 9. And the next, rather than being at index 16, it's going to be at index 15, etc. So here, this element of being at index 32 is going to be at index 36, which means it's going to fall in bank 4. This element, instead of being at index 64, it's going to be at index 72, which is going to fall in bank 8. So by adding this padding, we kind of shifted all the input elements a little bit to the right. They landed in different banks, and now we don't have any bank conflict when we're doing the access. Is this clear? Any questions? Okay, so now let's look at the second input array. So for the second input array, we have this input array that we loaded to the shared memory, and then logically the ones are going to iterate through the strips in shared memory. We have this strip in shared memory that we're now focused on, and every thread is going to load 2 parts of the strip from the shared memory to the registers. So let's focus on the threads are loading this of the input strip from shared memory registers. Again, here, all these threads are going to load the elements of the strip that go 0, 1, 2, and 3. These threads are going to load elements from the strip 4, 5, 6, and 7. These threads over here will load 8, 9, 10, 11, etc. Now, if this input tile is in row major order, right, these elements are going to be just 4 elements apart. So all of them are going to fall into different banks. So here we don't have any bank conflicts. Okay. By the way, this was by design, right? When we divided the tile across warps, right? We made the warps tall this way. We made the warp output tiles all in this way so that we can avoid conflicts here, right? But if we divided the block output tile in a different way, we could have divided the block output tile such that each warp takes a very long strip of the output tile. But sorry, a very wide strip of the output tile. But if we did that, we would have had bank conflicts. So when I was rearranging the tile to solve the coalescing of the stores issue, we kind of eliminated bank conflicts when accessing the second input tile in that rearrangement. Okay, is that clear? Any questions? Okay, so now let's talk about occupancy and how we can deal with occupancy. So software pipelining is an optimization that we're going to apply to deal with occupancy. But first, let me talk about why occupancy is an issue. So these advanced matrix multiplication kernels usually have very low occupancy because they use so many registers. Why do we use so many registers? So remember, we did register tiling for the output tile. So if we have a 64 by 64 output tile, that means every every thread is going to have 64 registers just for storing the output time. We also did register tiling for the input strips, so that adds more registers to our register usage. And another thing to remember is that we did a lot of loop unrolling. And when you do loop unrolling, what happens is that the compiler starts moving the instructions around to interleave them to minimize the dependencies between consecutive instructions so that you don't have stalls in the pipeline when you are doing your computations. And because of that, because of loop unrolling, you end up using a lot of registers to store the intermediate values. And because of these registers, you also get very high register usage. So for a typical matrix multiplication kernel, each thread ends up using the maximum allowed registers in CUDA. So the maximum number of registers that you're allowed to use is 255 registers per thread. And a typical matrix multiplication kernel is going to use 255 registers per thread. Okay. Now, when you use 255 registers per thread and you have a 64K register file per SM, what that means is that your occupancy is going to be limited to 256 threads per SM. Okay. Now, remember, the SM can have up to 2048 threads. So when you're using 256 threads in the SM, because your occupancy is limited by the registers, you're only going to be operating at 12.5% occupancy. Okay, which is very low occupancy. And it's not just low occupancy, you're going to only have one block, right? Because remember, we said we're going to have 256 threads per block. The reason we had 256 threads per block is that that's the maximum that we can have on the SM. Okay, so we're just going to have one block on the SM. And I'll remember this point because it's going to be important in a little bit. Okay. Okay, now this was intentional, right? We wanted to use a lot of registers in order for us to increase the arithmetic intensity to be compute bound. Okay, and the fact that we're compute bound, helps us fully utilize the cores. But having low occupancy is going to be an issue. What are the drawbacks of low occupancy? Low occupancy gives us two issues, right? The first issue is that we're going to have much fewer warps available to hide our core latency. Remember that the way GPUs hide latency is that when one warp stalls, you bring in instructions from another warp. When the other warp stalls, you bring in from another warp, and you keep bringing from other warps. The more warps you have, the better able you are to hide latency. So when I have very low occupancy like this, the hardware scheduler has much fewer warps to choose from when it wants to hide latency in the cores. Okay. The other drawback of low occupancy is that you have fewer warps available to issue memory requests to hide the memory latency. So remember, one of the advantages of high occupancy is having a lot of instructions to choose from in your cores. But another advantage is the more threads you have, the more memory requests you can issue at the same time. And that helps you fully utilize your memory bandwidth, right? You can't fully utilize your memory bandwidth if you have only a small number of threads because you're going to be limited by how fast you can issue memory operations. To be able to fully utilize your memory bandwidth, you need to make sure that you are sending a lot of memory requests at the same time to the memory so that you can hide the memory access latency. And to do that, you need to have a lot of threads. So when you have fewer threads, you're going to be able to issue fewer memory instructions simultaneously. And what that means is that you're going to be less able to hide the memory access latency. So these are the two drawbacks of low occupancy. Okay, now how do we overcome this, right? How do we overcome the fact that we're operating on low occupancy? Well, we need to resort to other techniques in order for us to hide the latency. Okay, and in fact, we've already done two things, right? The first one is loop unrolling. So when you do aggressive loop unrolling and you reorder the instructions, you are creating more distance between instructions that are dependent on each other. And what that does is that it reduces how frequently a warp is going to stall. Okay? And when you reduce how frequently a warp is going to stall, you reduce how often you're going to need to go and look for other warps to schedule. So loop unrolling already helps us with tolerating the latency in the cores. Another one is Vector loads and stores. So remember I talked about vector loads and stores and the importance of being able to issue more memory requests with fewer instructions. Well, this is precisely the reason. If I have fewer threads able to issue memory instructions, what I'd like for these fewer threads to issue memory instructions faster, and in order for me to fully utilize my memory bandwidth. And the vector loads and stores help us do that. They help the same thread issue memory instructions, load or store instructions at a faster rate in order for us to cope, to be able to have more memory requests in flight to be able to hide the memory latency. Okay, so these are two things that we've already done in order for us to hide the latency, to compensate for the fact that we have low occupancy. One more thing that we're also going to do is, well, a couple of things, our software pipelining and warp specialization. So these are also software optimizations that we can do in order for us to cope with the fact that we are operating at low latency. Okay, and let me explain what these are. So let's go back, and this is kind of a simplified version of the code that, by the way, any questions about these occupancy considerations before I explain software pipelining? Is it clear to everyone? Okay. So let's go back. So remember, the main part of our code is we had this loop over the input tiles. And in every iteration of the loop, what we're doing is we're loading two input tiles, we sync threads, and then we calculate the contribution of these input tiles, and then we sync threads, and then we keep repeating. Okay? So what happens is we're going to have this, right? We're going to have different iterations. In each iteration, we're going to have some instructions that load from global memory to shared memory. And then we have async threads. And then we're going to have some instructions that are going to compute, right? So here I load tiles 0. So A0 and B0 here refers to tile 0 of the A and B matrices, right? And then I sync, and then I'm going to compute the contribution of A0 and B0 to my output tile, and then I'm going to sync. And the next iteration, I load the next pair of tiles, and then I compute. Next iteration, I load the next pair of tiles, and I compute. Next iteration, I load the next pair of tiles, and compute, etc. Okay. Now, we were saying that all these optimizations that we did made our computation compute bound, right? Because I do much more compute than memory accesses. But that's not the full story. Look, so what we have over here is actually not a compute bound computation, but we have a computation that has phases, a memory bound phase and a compute bound phase. So over here, when we are doing this loading, from A0 to B0, we're using the memory, but we're not using the ALUs. So we have a memory bound phase. And then over here, when we're computing with the values that we loaded from memory, from global memory to shared memory, here our ALUs are busy computing, right? And our memory is idle. Okay. So we don't have a fully compute bound computation. We actually have a computation that has phases, a memory bound phase and a compute bound phase. Now, because of what we did, the compute bound phase is going to dominate the memory bound phase, but we still have phases. The memory bound phase is not being hidden by the compute bound phase. Now, ideally, what we would like is we would like for the ALUs and the memory to be busy at the same time so that all the memory accesses are hidden behind the compute. Okay, that's what we would like to have ideally. And so we wanted both the memories and the ALU to be busy. And if we had multiple blocks on the SM, that would be the case. Because when one block is in its memory bound phase, another block will be in its compute bound phase, and vice versa. So, and as long as the memory bound phase is less than the compute bound phase, right, the SM is always going to be busy with compute, either from this block or from that block. Okay, so if we had multiple blocks, this would not be an issue. But because we have low occupancy and because we only have a single block, right, we're not going to have a fully compute bound computation. We're going to have these phases where we have memory bound, then compute bound, then memory bound, then compute bound, then memory bound, then compute bound. Okay. So because of that, and we don't like that, right? We want to be able to hide the memory operations behind the compute operations so that the SM is always busy computing, because that's how we maximize how much we utilize the hardware. Now, to be able to do that, what we need to do is we need to overlap the compute operation, the memory operations with the compute operations in order for us to be using the memory and the compute at the same time. Now, can we do that, right? And the answer is yes, we can. And let's see how we can do that, okay? So let's take a look. So if we look at this iteration, can I overlap the loading of A0 and B0 with the computation of A0 times B0? No, I can't. And the reason is that I need to wait for the load to finish before I do the computation. However, can I overlap this computation with the loading of the next tiles? And the answer is yes, I can. And the reason I can is because this computation is independent of these next tiles. So what I can do is while doing this computation, I can start loading the next tiles. But the way I've written the code over here prevents that from happening. And let's look at why. So if we look at our sync threads, we have two different kinds of sync threads here. We have the sync threads that are waiting for the load before doing the compute. And we have the sync threads that are waiting for the compute to finish before doing the next load. The first sync threads is enforcing what we call a true dependence. It's a true dependence because we need to wait for the data to be loaded before we can compute with the data, right? The dependence is a real dependence. The compute truly depends on the load. But the second sync threads is enforcing what we call a false dependence. We don't really need to wait for the computing of the first tile to finish before we start loading the next tile. The only reason we are waiting is because we are using the same memory buffer to store these input tiles that we are using to store these input tiles. And for that reason, we are having to wait for this compute to finish consuming the input tiles before we can overwrite that memory location with the same input or with the new input tiles. And this is a false dependence, right? We don't really need to wait. We're only waiting because we're waiting for that memory to be consumed before we can reuse it. And the solution for this is simple. The solution for this is something called double buffering. And the idea of double buffering is instead of using the same memory location for tiles A0, B0 and tiles A1, B1, I can use a different memory buffer for the odd tiles and a different memory buffer for the even tiles. And that way, after I load tiles A0 and B0, while I'm computing A0 times B0, I can start loading A1 and B1 into a different memory location. And that way, I can get rid of this sync threads because now I no longer need to wait for A0 and B0 to be consumed before I write A1 and B1. Okay, so using different memory buffers helps us eliminate the sync threads right here. However, we still have an issue that prevents, so now we no longer have the sync threads, which means that these instructions and these instructions can be overlapped with each other so that I can do the memory instruction, I can use the memory to do the load while using the ALUs to do the compute. But what's still preventing this from happening is the fact that these instructions and these instructions are in different iterations. So we can't really interleave instructions across the iteration boundary. So to do that, what we do is something called software pipelining, where because the instructions need to be kind of come after each other in the same iteration for me to be able to interleave them. So what we're going to do is rather than having the iteration load, sync, and then compute, we're going to start the iteration here where the iteration computes and without a sync is going to load the next tiles. And when we do this, now we have exposed the compute and the memory instructions to each other without a sync thread separating them. And what that does is it allows the compiler to reorder the instructions, to interleave the memory instructions and the compute instructions with each other so that during this iteration, we're using the memory and the compute at the same time. Okay, is that clear? Any questions? Okay, so this is software pipelining. Now, one thing about software pipelining is that it relies on the compiler to interleave these instructions, right? So once I've rewritten my code to where I have in the same iteration, I'm computing and I'm loading the next tile, the compute and the load are independent. The compiler now comes and it starts interleaving these instructions with each other. So this relies on the compiler to do a good job at interleaving these instructions. But the problem is that the compiler doesn't always have an accurate idea. The compiler can make good estimates of how long each instruction needs to take and how many instructions I need to put between these two instructions that depend on each other to make sure that I have no stalls. But there's always a limit to how much information the compiler has, right? The hardware is usually better at interleaving instructions. Okay, so what can I do to have the hardware interleave instructions? GPUs don't have out-of-order execution; they do in-order execution. So, but what GPUs do is that they can. What the hardware is good at is interleaving instructions from different warps. And if I want the hardware to interleave the compute instructions and the memory instructions based on how these instructions behave at runtime, right, rather than relying on the compiler, what I need to do is I'm going to have to put the compute instructions and the memory instructions in different warps. And that's what warp specialization is. So far we've relied on the compiler to interleave the memory and the compute instructions in order to hide the latency. But the compiler has limited knowledge. So what we can do is we can apply warp specialization, where we have some warps in the block be responsible for computing the output tiles, and then a different set of warps be responsible for loading the next set of input tiles from the global memory to the shared memory. Okay, and then rely on the hardware to interleave the execution of these different warps during the code. So if we go back, actually, no, I just remember I don't have the code for this visible. Okay, so here we're allowing the hardware to interleave the compute and memory instructions from the different warps dynamically. So all this we have done in order for us to cope with the fact that we're operating at low occupancy because of our high register usage. Any questions? Is everything clear? Okay, so at last I'm going to talk briefly about some specialized hardware units, especially the tensor memory accelerator and the tensor cores. So for the tensor memory accelerator, you know how we spoke about the importance of overlapping the memory access with the compute. Okay, and we did that by having different first by interleaving the instructions, and later by having different warps. Some be responsible for compute and some be responsible for load for the memory access. Well, what the tensor memory accelerator is, this came out in recent GPUs, is it's a data copy engine that can be used for transferring large blocks of memory from the global memory to the shared memory. Okay, and what that means is that instead of having to rely on executing load instructions and store instructions, even vector load instructions and vector store instructions to transfer the data from the global memory to shared memory, what we can do is we can just have the tensor memory accelerator do that transfer for us. We tell it, hey, we want to transfer this much data from global memory to shared memory. Can you please do that for us? And then this engine will take care of doing that copy in the background while the cores take care of computing. And this further improves how much we can overlap the compute with the memory access so that we can completely hide the latency of the memory access and make sure the compute is always busy. So there's two advantages of using the tensor memory accelerator. The first is that instead of busying our compute cores with doing data copy instructions and the index calculation for those data copy instructions, right? We offload those to the tensor memory accelerator so the compute cores can focus on doing the matrix multiplication computations. So this gives you better overlap between the computation and the data transfer. But then also it avoids using registers. So remember when we load from global, when the threads load from global memory to shared memory, the way they do it is by loading from global memory into registers and then storing from the registers to the shared memory. And also when you store from shared memory to global memory, you load from shared memory into the registers and you store from the registers into the global memory. So when the threads are taking care of the transfer between global memory and shared memory, they're using registers all the time. However, when the tensor memory accelerator does it, it's not using any of the registers, and that frees up a lot of registers for the threads to use for improving the computation. Okay, so these are important advantages of using the tensor memory accelerator. And of course, we have tensor cores. So we've done a lot of so far. We've been using the regular FP32 compute cores in order for us to do these computations. But CUDA GPUs also come with specialized tensor cores that can perform so these small, when we multiply two small tiles to get another tile, there are tensor cores that allow us to do these computations at a much faster rate. So instead of having to be limited by multiply, add, multiply, add, multiply, add instructions, we just have one instruction that does a very big matrix, not a small matrix multiplication, but bigger than a single multiply add in using just one instruction. Okay, and typically these are used in libraries like CuBLAS and Cutlass. So all the techniques that I talked about in this lecture, these advanced techniques, they're widely used in CUDA libraries like CuBLAS and Cutlass. And actually, this image right here that I kind of I had a very similar image that we went through as I was going through the different optimizations. Right, this image right here comes from the Cutlass documentation. So it kind of shows you that what we've explained in this lecture is inspired by a lot of the techniques that are used in Cutlass to optimize the matrix multiplication. So typically, you don't need to implement matrix multiplication yourself on a GPU, right? All these optimizations that I explained today, these are already implemented and very well optimized libraries like CuBLAS and Cutlass. So you rarely need to implement a matrix multiplication on your own. It's always better to use the libraries. However, the reason it's kind of interesting to go through this lecture is first you understand how these libraries work so that you can use them more effectively. But also, matrix multiplication is such an important computation, and it's a great way to showcase a lot of these different optimizations that I've presented in the lecture that you may be able to use in other computations that maybe don't have a library and that you're trying to optimize. So kind of part of the objective of this lecture was not just to teach you how to optimize matrix multiplication, because you're unlikely to do that, but it's to show you how to think about applying different optimizations to push the performance of a computation to the limit to make it as compute bound as possible and deal with all these memory access issues and these occupancy issues. Okay. And with that, I am done with the lecture, and I'm happy to take any final questions if anybody has any.
Yes, one question. We I was previously familiar with the normal, just naive tiling with n by n tiles and output tile. All of these other optimizations that you described, how big of a speed up can you expect from them?
You can expect very significant speed up compared to the. I don't have a number in my head, but you can expect, an order of magnitude speed up from these optimizations, because the one that uses shared memory tiling is still, it's still limited by memory bandwidth. You're not reaching the kind of the highest utilization that you can achieve for of the compute cores. But with these optimizations, you really get the memory bandwidth out of the way, and that's where you reach a point where your cores are just flying with multiplies and adds. So you can expect quite a significant speed up from these optimizations. I apologize, I don't have a number in my head. But if you're interested, you can compare the shared memory implementation that you had with just calling CuBLAS and comparing their performance, and you can kind of get an idea for what the difference is like.
All right, thanks.
Yeah, welcome.
Okay, is there any questions? Any other questions? All right, unfortunately, we are running out of time. So, and I asked my question during the lecture, and it was a very interesting presentation, in my opinion, since it gave us a lot of ideas about what's happening and what's going on under the hood in these like high performance linear algebra libraries. And I just want to emphasize here that this presentation focused on single GPU optimization, but there are also like if your input data or your matrices are so large, you probably want to distribute them into different machines, and then that comes to distributed linear algebra. And also you have a lot of optimization there. Okay, so with that, I would like to thank you very much, Izzat, for the very nice and interesting presentation. And we hope we can have you in other courses as well, like in the next periods. So thank you very much.
Yeah, my pleasure. Thanks for the invitation. It's nice to meet you all.
Yeah, thank you. Okay, so I think we can wrap up this lecture, and I hope it was useful for everybody. So have a good rest of the day, and see you next time.
Thank you. Bye bye.
Thank you. Bye.
Bye. Bye.